Hi, it's Miss Heaton signing in to talk with you about Ka, which is basically just equilibrium applied to acids. We'll talk about bases later in class, but first I want to start by reviewing what Miss Ewald elegantly covered in her first screencast or earlier screencast about pH. She mentioned these 6 strong acids. Now remember, anytime you have these, they dissociate completely. So here's a visual of what it looks like. Here's a strong acid. All of the H plus has separated from the acid part. So there's H pluses and, oops, that would be an H plus. So they've completely separated. For a weak acid, most of the acid is still paired together, but a few of them have broken apart. So weak acids basically are just not dissociated. We're going to be doing calculations that involve weak acids where you can't assume that the pH is the same as the concentration of hydrogen ions. One thing I want to point out before moving on. This is different than concentrated versus dilute. Concentrated means you have a whole bunch in a small space. Dilute means you have like 3 in a small space. It has nothing to do with whether the particles are still stuck together or broken apart. Let's focus in on these weak acids. These are the acids that are still mostly stuck together, not dissociated. They can have a range of strengths. You could have the bodybuilder weak acids that have a pretty large Ka, relatively speaking, maybe on the order of like 1 times 10 to the negative second. That actually means that about 1% of them are broken up, and 99% of the acid is still together. On the other hand, you could have something with a super duper small Ka. Something like this would have only a very small percent broken up. So we're talking on a really, really small scale here. Not very much has dissociated or broken apart, but it's enough to affect the pH in a way that we can't calculate it using our normal equations. We're going to use a Ka value to quantify how much that acid has dissociated. Like I mentioned earlier, this is just like KEQ, but now we're applying it to an acid. So if we have an acid, HA, A stands for whatever the anion is, and it reacts with water, which is a pure liquid, if it's an acid, it's going to donate its proton to H3O plus and leave behind A minus, and the water will gain that proton and turn into H3O plus. This is kind of the generic equation for an acid reacting with water. You can replace the A with whatever the anion is. Now, if it was a strong acid, that means all of the HA would break up. So it would all be H3O plus and A minus. So the Ka would be like a really, really big number. Imagine the biggest number you can picture. It would be 100 over basically 0 because none of it would be left undissolved. Oh, let me back up a second. We probably should have written the Ka equation for this. Ka would be products, so H3O plus times A minus, over reactants, which would be HA. And would we include H2O? No, we wouldn't, because it's a pure liquid. So if it's all broken up, you'd have lots of numbers, lots of concentration with your products, and very little, or virtually 0, with your reactants. So it would be a huge Ka value. We're not going to deal with any strong acids this way. You'll use our old pH calculation method. Before we move on, though, bases can be strong or weak. We'll deal with that at a later date. Okay, let's dive right into a calculation here. Here's the kind of problem where you would need to use Ka. You're asked to calculate the Ka when you have a 0.1 molar solution of some acid, and so that's your initial concentration, and you're finding that its pH at equilibrium is this number. First thing you always want to do is start by writing a balanced equation. So your acid, which is aqueous, will react with water. You'll put it into water, and it will turn into H3O plus and A minus, which is aqueous. So your Ka expression would be H3O plus, same as we wrote before, times A minus over HA's concentration. So there's your generic Ka expression. You can do an ice chart just like we did in the last unit. Hey, who knew that there are so many applications for K? It's pretty cool, isn't it? So we know that our initial concentration of HA is 0.1, and we have none of our products initially. We know that our change rho will be minus x, and plus x, because the coefficients are all 1. So at equilibrium, we'll have 0.1 minus x, x, and x. Let's see if we know any other information. Oh, well, we know that pH at equilibrium, after it's dissociated, is this number. So that's going to go into our solve area. pH is 2.38. So if the pH is 2.38, can we find anything that goes in here? Oh, look at this. We know that the concentration of H3O plus is 10 to the negative pH. So we can use that to find the concentration of H3O plus at equilibrium. So if we do 10 to the negative 2.38, hey guys, this is where you bust out your calculators and try it on your own. Make sure that when you type that in, you get 0.004169. That would be your concentration of H3O plus at equilibrium. So wait a second, that's what x is. So if x is 0.004169, we could plug that into our Ka expression and find out what the equilibrium constant is for this acid. We do 0.004169, H3O plus. Now that's also going to be the value of A. And on bottom, we do 0.1 minus that number. So into your calculator, which you are definitely using, right? You would type that in, and you should get 1.81 times 10 to the negative fourth. Now, I just did that real quick, so I hope that I did that right. If you discover that I did it wrong, I will have a special prize for you in class. Okay, one more example here. This is kind of going the opposite way. If you are given the pH, oh no, we're trying to find the pH this time. Find the pH if the solution is this concentration and the Ka is this number. So first step is always to write your balanced equation. So here's our acetic acid, which by the way is the main ingredient in vinegar, which is used to dye Easter eggs. So we've got acetic acid reacting with water to make H3O plus and C2H3O2 minus. Notice that this time we've replaced the A with the specific anion that we're using. We'll write the Ka equation. That'd be products over reactants and then we'll fill in our ice chart. Leaving out the water because it's a pure liquid and it will never get included in our equilibrium calculations. So our initial concentration of acetic acid was 0.3. We always start with 0 of our products. Our change rule will always make us lose what we start with and gain what our products. And so it'll be 0.3 minus x, x, and x. So we can plug that into our Ka expression. So Ka will be x times x over 0.3 minus x. Oh, and we were given the Ka value this time. So we'll plug that in for Ka, 1.8 times 10 to the negative fifth. Okay, what are we trying to find again? Oh, that's right, we're trying to find the pH. Now, if we're looking for pH, what we did before is we said that pH is the negative log of the H3O plus concentration. Well, we did the opposite equation of that. But basically, if we could figure out what x is, we could plug it into this equation and find the pH. So, we have some mathematical complicatedness going on here. We have a couple options for solving for x. We could use the approximation or the quadratic. Let's see if we can approximate, because that is easier. So what we'll do is we'll take our initial concentration and divide it by the Ka value. Our initial concentration, okay, so we'll plug in our initial concentration of 0.3, our Ka value, which was 1.8 times 10 to the negative fifth. And if that number is bigger than 1,000, then we can do the approximation. So when we divide that, we see that we get this huge number, which is definitely bigger than 1,000. So yes, we can approximate. And that means that x is virtually 0 in our denominator. So plugging that in over here, that'd be x squared over 0.3 minus virtually 0. So then we're just going to do some very simple algebra. Multiply both sides by 0.3, and you'll get 5.4 times 10 to the negative 6th equals x squared. Square root that, and you find that x is 0.00232. So that, from our table, was the concentration of H3O plus. So we can use that then to find the pH. So the pH is going to be the negative log of 0.00232. So calculate that, and you will have your pH. I'm going to make you do that on your own. Get that calculator out, get to work, calculate Ka, come to class tomorrow, and we will continue to practice. Happy Kaing!